Hello everyone, my name is Jair Acosta and I'm going to present the paper entitled Optimizing Multi-Circuit Transmission Lines for Single-Phase Auto-Reclosing made by Professor Tavares, Professor Gold, and me. Okay, let's begin. Well, because of the increasing of the population, industries, services, and technologies, there is a continuous growing on the power demand that must be faced by increasing the power capacity of the transmission lines at the lowest cost. Additionally, because of the strong environmental regulations that can delay the transmission line projects, the design of new transmission lines should be done using the lowest right of way. Then we could avoid situations like this in which, because of the lack of space, the population put themselves in a dangerous position. Finally, we should also try to get a balance between the tower height and the right of way. So, aiming to solve the problem of transmitting more power in a narrow space, some solutions have been proposed by different researchers. The first one is the use of non-conventional single-circuit transmission lines. These lines are based on the fact that if you increase the quantity of conductors per bundle, or the bundle size, or if you decrease the distance between phases, it is possible to increase the power capacity of the transmission lines. The second alternative is the use of multi-circuit transmission lines, which highly reduce the right of way and allow transmitting more power that is proportional to the number of circuits in the same tower. And for these solutions, there are already many investigations that show the advantage and disadvantage of this type of line. The last alternative, which is the one that we are using in this research, is to use non-conventional multi-circuit transmission lines combining the characteristics of the previous alternatives. So, with the previous alternative, it is possible to obtain transmission lines like the one in blue, which has a higher power capacity and a lower growth compared with conventional parallel single-circuit transmission lines. However, to be able to implement these lines in practical situations, it is necessary to ensure that the lines have a good behavior for different situations, like in the case of the single-phase auto-reclosing that depends on the secondary arc current. Okay, so what is the secondary arc current? Well, when we have a fault and we do a single pole tripping, we will have a residual fault current, known as secondary arc current, that is maintained by the capacitive coupling between the phases and the ground. And depending on the situation, the fault can be maintained for a really long time, and it will be necessary to perform a triple tripping to completely eliminate the fault. The problem with this is that we will completely lose the power flow. So the ideal situation is to have a current small enough to be extinguished by itself. To do that, what is normally done is to add a neutral reactor in the common point of the phase reactors. This scheme is known as four-legged reactor, and the parameters can be calculated with the Kinbach formulation. In this figure, you can see the waveform of the fault current for a single line to ground fault with single pole tripping. So during the fault, we will have a primary arc with dozens of kiloamps, and after the single pole tripping, we will have the secondary arc current with dozens of amps that after a certain time will be extinguished by itself. Well, according to the literature, the secondary arc current in a 400 kV transmission line have a high probability of arc extinction for a dead time of 500 milliseconds if the steady-state secondary arc current and the transient recovery voltage are inside the zone presented in this figure. But now, if we intend to analyze lines with different voltage levels, it is necessary to extrapolate these values, as we did in this table. Taking into account the previous limits, we introduced the secondary arc current as a constraint in the mathematical model that describes the multi-circuit multi-voltage optimization problem presented in our previous research and summarized in this mind map. So we have four objective functions that are the line power capacity, the line cost, the right of way, and the tower height, and a set of constraints that can be mechanical or geometrical, electrical, or auxiliary. And inside the electrical constraints, we have restrictions related to safety distance, electric field, audible noise, ampacity, and the new secondary arc current constraint. Then this mathematical model was solved with an optimization algorithm that in this case is the NSGA2. That is a multi-objective optimization algorithm based on evolutionary computing. Formally, we are solving a maximization multi-objective problem with 4 objective functions and a set of decision variables that can be either integer, permutation, or real. So for the decision variables, we have the tower type, the circuit type, the number of conductors per bundle, the conductor type, the phase sequence, the circuit height, the x and y coordinates of the circuit centers, the distance between phases, an auxiliary decision variable, and the position of the conductors according to the circuit type. And as presented before, there are a set of constraints, and in case of overcome a restriction, a penalization is applied to the objective functions. And as you can see, the penalization is proportional to the degree of violation of the restriction. Now, to calculate the secondary arc current, it is necessary to put the lines inside an electrical system. In this case, the lines were introduced in a system like the one presented in the figure, that is composed by equivalent sources at the sending and receiving end, adjusted to transmit 90% of the line power capacity. They are also connected to a compensation of 70% with neutral reactors calculated with the Kimber formulation. And in our case, the lines are long multi-circuit, multi-voltage transmission lines of 350 kilometers with a full transposition cycle of 1/6, 1/3, 1/3, 1/6. Okay, since we are optimizing the lines including the secondary arc current, it will be extremely time-consuming to calculate the SAC with MTP simulations. Therefore, we modeled the entire system using two-port network elements, including the source equivalence, breaker status, compensation, transmission lines, transposition, and faults. If we reduce the system, we can see that the secondary arc current is just the sum of the current that is entering into the fault two-port network element. And using this approach, the secondary arc current was obtained for faults in each phase along the line. So the system was modeled in phase domain. Now we will see the results of optimizing the transmission lines with our proposal. So to observe the advantage and the scalability of our proposal, we optimized multi-circuit and multi-circuit multi-voltage transmission lines. In these figures, we can see at the left a double circuit transmission line with two circuits operated at 500 kV, optimized considering the secondary arc current as a restriction. And on the right side, we have a double circuit transmission line optimized without considering the secondary arc current as a restriction. Now, if we compare the SAC values, we can see the advantage of our proposal. So it is evident that the SAC values are smaller in the line designed considering the secondary arc current as a restriction. In this line, we obtained a maximum secondary arc current value close to 50 amps, whereas in the line designed without considering the secondary arc current as a restriction, the maximum SAC value was almost 110 amps, which is above the limits for a successful single-phase auto-reclosing. Now, to show the scalability of our proposal, we also optimized multi-circuit multi-voltage transmission lines. Here we have at the left a double circuit transmission line with one circuit operated at 500 kV and the other circuit operated at 750 kV, optimized considering the secondary arc current as a restriction. On the right side, we have the same case with the difference that the lines were optimized without considering the secondary arc current restriction. Now, if we observe the secondary arc current values, we can see a similar behavior than in the case of the multi-circuit transmission line, showing the scalability of our proposal. Okay, since the behavior is similar in both cases, the following analysis will be shown just for the lines with two circuits operating at 500 kV. Previously, we observed that the new lines can greatly reduce the secondary arc current. However, obtaining that reduction can be done without an associated cost, and in this case, the cost was increase the tower height and reduce the power capacity. But at the same time, it was possible to reduce cost and right-of-way. So, as you can see, everything related to multi-objective optimization problems is a trade-off, and we need to choose the best alternative according to our preferences or requirements. Also, if you compare the transmission lines, you can see that the shape in both cases is quite different. Thus, observe that the line in the left has one circuit in a delta configuration, meanwhile the other circuit is in a horizontal configuration. Also, we can see that in both circuits there are 4 conductors per phase. On the other hand, the line on the right side has 2 circuits in a horizontal configuration. And in this case, we have five conductors per phase. Therefore, to achieve the secondary current reduction, it is necessary to use towers with special configurations. Now, if we compare the zero sequence admittance, we can see that the line optimized considering the secondary current has values that are up to 24% smaller than the other line. And certainly, this is an important characteristic that is helping to reduce the secondary arc current. Now, if we see at the neutral reactor parameters calculated with the Kimber equation, it is evident that the values for the line optimized considering the secondary current as a restriction are bigger, which is caused by the special configuration of the line. Also, observe that the voltage at the neutral reactors is higher. However, the values are just slightly higher, which do not compromise the normal operation of our line. Now, if we observe the behavior of the secondary current and the transient recorded voltage when applied faults along the lines and in each phase, it is evident that the response of the optimized line that considers the secondary current as a restriction is better. So if we observe the limits that are marked with a red line, we can see that the SAC and TRV values are under the limits in all cases. On the other hand, the response of the line designed without considering the secondary current as a restriction that is located at the right side shows that the SAC and TRV values are outside the limits in all the cases. Now, if we zoom the secondary current response of the line that doesn't consider the secondary current as a restriction, we can see that the maximum SAC value in each circuit was produced by faults close to the receiving source, but produced for faults in different phases. If we also amplify the secondary arc response of the line that considers the SAC as a restriction, the behavior is different. In this case, as you can see, the maximum SAC value was produced by faults close to the sending source. Because of this, it is evident the importance of calculate during the optimization process the SAC in both line ends and in each phase. Finally, since the optimization process was done with two-port network elements, still it is necessary to validate the secondary current response with an ARC model. So if we use the A.T. Jones model, we can see that indeed the optimized line that considers the SAC as a restriction presents a faster arc extinction time, that in this case was approximately 41% faster. Finally, if we also confirm the TRV value, we can see that it is also smaller in that line. However, it is important to highlight that the arc extinction times obtained with the Jones model are smaller than the one that we expected. So we suggest for future investigations to develop a more accurate model. To conclude, we can say the following. First, the inclusion of the secondary current as a constraint produced important reductions on the secondary current that are up to 64% smaller, helping to make feasible the single-phase auto-reclosing in the optimized multi-circuit and multi-circuit multi-voltage transmission lines. Second, the reduction of the secondary current can be achieved using four-legged reactors calculated with the Kimber formulation without requiring a special reactor configuration for multi-circuit transmission lines. Third, the validation with an ARC model showed that the proposed lines indeed produce faster arc extinction times. However, still it is necessary to perform tests with more accurate models. And finally, the methodology presented in this research can be used in any system, yielding optimized transmission lines ready to perform the single-phase auto-reclosing with success. Thank you for your attention, and thanks to all the supporters that made possible this research.